Yeah, so I'm going to talk about the tortoise and the hare, or slow versus fast earthquakes. And we're going to start at the beginning. So we're going to start by talking about what an earthquake is. And that will, then we'll use that to talk about what makes an earthquake fast versus, or what makes it slow. And then we'll talk about why these newly discovered slow earthquakes might be important and how they might tell us new things about fast earthquakes, the sort of earthquakes that we worry about. So, as was mentioned, I teach at Stanford University. I'm giving this lecture as part of the IRIS SSA Distinguished Lectureship. So it's an interesting time to be an earthquake seismologist. 7 earthquake experts, including 2 people that I know fairly well, were convicted of manslaughter a couple of weeks ago because of the way what they said was interpreted. So I'm going to be very careful in what I say to them, because while the recording, while I'm being recorded. But if you want to buy me a drink afterwards, I can. Unabridged story. So what is an earthquake? Well, I'm going to illustrate this with a particular earthquake, one that happened in Japan that was a landmark earthquake in the history of earthquake science. The Japanese refer to it as the Hyogo-ken Nanbu earthquake, or the south of Hyogo Prefecture earthquake. It was a magnitude 6.9 earthquake. An earthquake of that size occurs about once a month, maybe a little more frequently, somewhere on Earth. And for the most part, they don't generate a lot of press coverage. This one was different, though, because of where it occurred. It occurred in Japan, not on the subduction zone, but above the subduction zone. It ruptured from the Awaji Strait here. So this is the main island of Honshu. This is Shikoku here. We'll return to Shikoku later in the talk. Here's Awaji Island. The earthquake started at the strait in between the two. It ruptured mostly to the southwest, so most of the energy was directed to the southwest, about 2/3 of it. About 1/3 was directed to the northeast. The rupture came to the Earth's surface on Awaji Island. There's a museum that I'll show you in a second that is built to preserve the fault scarp. The rupture did not come to the surface to the northeast under the city of Kobe. So this is what the surface rupture looks like in cross-section. So the Japanese built a museum. They made a tourist attraction out of this fault scarp. You can see it's, to first order, it's a cut through the earth, separating 2 walls of the fault. There's a vertical component of offset that happened during the earthquake within the space of a few seconds. You can't see it here, it's not clear, but there's actually a larger horizontal offset of something like 1.5 meters to 2 meters. So this slip happened suddenly, over a matter of seconds, and it is this slip that generated seismic waves. But when people like me talk about an earthquake, we tend to think not about the waves, not about the shaking, but about the sudden fault slip that generates that shaking. I think that difference of reference leads to some misunderstandings between earthquake scientists and the public. So from my point of view, usually when I talk about earthquakes, I think about earthquakes as the sudden fault slip itself. That is just what we call the source process, rather than the more rational definition, which is probably what most people think of the earthquake as, is the actual shaking, so the seismic waves as they propagate through the earth. So now I'm going to show you the shaking from this earthquake. I'm going to show you a video. It's my favorite video for trying to communicate what an earthquake is like. And it all goes by pretty quickly, so I'm going to show you a few still shots and explain what you're going to see. So the earthquake happened at 5:46 in the morning, a cold January morning, so it's before dawn. And what you will see on that table is initially just a weak shaking of the objects on it. So you won't see anything fall over, but you'll see them jiggling. That is the P wave, the fastest first arriving wave from the earthquake. just a few seconds later, 2 seconds later, it becomes apparent that there's a guy sleeping in the lab, or at work, in this building in Kobe. He wakes up, and it's just 2 seconds between when the shaking first begins and when this guy wakes up. So he wakes up pretty quickly, and he sits up, and if you look closely, you'll see him. And he wraps his head in a pillow, and at that time, there's much stronger shaking from the S wave and the near field waves. He's very close to the earthquake eruption. So 4 seconds after that weak shaking, the motion is strong enough to start knocking over objects and becomes dangerous. So this is sort of the earthquake conundrum. There's no obvious warning before an earthquake. The onset is sudden, and it's only a matter of seconds before the shaking gets strong, if you're close, strong and dangerous. So now I'm going to play that video. So weak shaking on the table. Guy wraps the head around his pillow, the bookcase comes down. No, he wraps the pillow around his head. And the bookcase comes down. This earthquake, the rupture on the fault, the amount of time that the slip was occurring, spreading across the fault, was something like 8 to 10 seconds. It's typical for a magnitude 6.9 earthquake. So it's for that amount of time, the waves are being generated. And, well, it's gone dark here, but the shaking, the strong shaking in the wave, in the earthquake, is over in a matter of 10 to maybe 15 seconds, because the waves travel at different speeds and they spread out a little bit. So I'm going to play it one more time, and then we'll move on. So that illustrates in a way that you can't really illustrate with words just how sudden the onset of an earthquake is. And the reality is that if you're not prepared for an earthquake before it starts, there's very little you can do to get ready. The advice in this country and in developed countries where buildings won't fall down, if an earthquake starts, is to drop cover and hold on. Okay. This earthquake happened in 1995. It's known as the Kobe earthquake. It's known as the Kobe earthquake because it devastated the city of Kobe, Japan, killed over 6,000 people in a matter of, the shaking lasted something like 10 seconds. It caused, this number is very uncertain, but it is thought to have caused $200 billion in direct economic losses. That does not, that's just things that break because of the earthquake. It does not include the ripple effect through the economy as the supply chain is disrupted. It does not include the long-term effects on Kobe, which were profound. Until the March 2011 earthquake in Japan, this was the costliest natural disaster in history, period. It's now been superseded by the 2011 earthquake, for which similar estimates are something like $300 billion in direct losses. Social scientists distinguish between disasters and catastrophes. They're both obviously bad things, but disasters are disasters that people and communities recover from. Catastrophes are disasters where the damage is permanent. And I was at Kobe for the 15th anniversary of this earthquake a few years ago, and the city looks like it's recovered. But at the time of the earthquake, it was the busiest port in all of Asia. It is now only the 4th busiest port in Japan. Because they were not able to reconstruct the port quickly enough, business went elsewhere, and it's never coming back. So Kobe has changed permanently for them. This earthquake was a catastrophe. So the response of the Japanese to that earthquake, the emergency response, has been criticized. They did not realize just how bad it was in Kobe immediately after the earthquake, and so help was slow to arrive. However, their longer-term response has been, from a scientific point of view, absolutely magnificent. They took that earthquake as a message that they had to redouble their efforts to understand earthquakes. This included, perhaps most importantly, a new openness in sharing data among different institutions in Japan, and also internationally with people people like me who study earthquakes wherever we can get the best data from. They coupled that with a renewed emphasis on earthquake monitoring, so measuring quantities associated with crustal deformation that leads to earthquakes, measuring very faint signals from very small earthquakes, deploying instruments that are capable enough to stay on scale even with the very largest earthquakes. And the slow earthquakes that I'm going to talk about in the remainder of my talk, most of the discoveries, the majority of the discoveries of slow earthquakes and associated phenomena were made in Japan and were made as a consequence of this monitoring effort that followed the Kobe earthquake. So this was a really important earthquake in history of earthquake science. What's shown here, this is the Japanese archipelago. Each red dot is a seismic recording station, a particularly sensitive one. This is a situation before the Kobe earthquake. There were a lot of red dots. They did a pretty good job of earthquake monitoring. Different monitoring networks did not necessarily share data, so they didn't get all of the value out of the data that they could have. After the earthquake, they shared all the data. They also constructed a new seismic monitoring network known as HyNet, which consists of over 800 now borehole seismic stations. So these are buried at least 100 meters in the ground. They're away from sources of seismic noise like human activity. So they allow us to see weaker signals from smaller earthquakes than would otherwise be possible. And new discoveries have come from this investment that they made. So that, and as a direct consequence of that earthquake, I and others were able to make discoveries about a new sort of family of earthquakes known as slow earthquakes. So what are slow earthquakes? We've talked about what earthquakes are. They're the sudden slip on faults and the shaking that's associated with them. We're going to go through 3 speeds that are associated with earthquakes. You got a taste of some of those in the multiple choice questions at the beginning. One is the speed of the slip. That's how quickly the two sides of the fault slide past one another at a point. Another is the speed of the slipping front. Excuse me. That's how quickly the boundary between the slipping region and the not yet slipped region propagates. That's orders of magnitude faster than the slip speed. And finally, the speed of seismic waves. That's how quickly the P and the S and other seismic waves propagate through the Earth's crust and mantle. So the speed of slip represents how fast the two sides of the rock move relative to one another. And this turns out to be very difficult to measure, but from what we can tell, it seems to be in the range of 1 to 10 meters per second. So that's about as fast as a sprinter run. So that's one speed associated with earthquakes. I'm going to stop this. This is an animation of a supercomputer simulation of an earthquake on the San Andreas Fault. And you're looking at 2 things. So there's the western part of California didn't just fall into the ocean. It was offset relative to the eastern part, so you could look at a cross-section of the vertical San Andreas Fault shown in gray. And what's shown with the sort of rainbow-hued color table is the slip rate, so how quickly the two sides of the fault are slipping relative to one another in this simulation. And so this boundary out here in front between the gray part that hasn't slipped yet and the part that's behind it that is slipping, that moves not meters per second, but kilometers per second. So typically as fast as a missile, say 2 or 3 kilometers per second. So I'm going to run this thing. And in this simulation, which is faster than real time, the time scale is being counted off up here in the upper right. This is for an earthquake that would rupture the entire southern San Andreas Fault. The simulation was done on the Jaguar supercomputer. I think it's at Oak Ridge. It's one of at the time, it was the fastest supercomputer in the world. It's not the fastest any longer. But these kind of simulations demand that kind of high performance computing. And so this is typically, even though that's a simulation, this is typically the sort of rupture speeds that we see in earthquakes, several kilometers per second. And what I'm going to show you here is a simulation of the 1906, it says magnitude 7.8 earthquake, but the correct answer is 7.9. So this simulation was done, actually the slip model that goes into this is a magnitude 7.9, so it's just mislabeled. This was done by Brad Agard of the US Geological Survey in Menlo Park. It's another computer simulation. This one is shown in two ways. One is in map view here. So this is California, rotated at an angle. The earthquake started off Ocean Beach, I think, and ruptured both to the south and to the north at a few kilometers per second. And as it ruptured, the seismic waves spread out from that rupture. And what's going to be shown here is the motion of the ground in Santa Rosa as the waves approach. Santa Rosa is built on a sedimentary basin, a shallow sedimentary basin. Sedimentary basins have the unfortunate property of focusing and amplifying seismic waves. They tend to be popular places to build cities because they're flat and easily, the construction on them is easy. However, when earthquakes happen, that structure works against you. What you will see as we propagate this forward in time, and this one does run at real time, what you will see is the waves approaching us. First, the fast propagating P waves. They're shown with the low amplitudes in blue. They will be followed by larger S waves and surface waves. And you will see a sort of converging of these wave fronts happening right now, right here in Santa Rosa. And you'll see that the intensity of shaking, shown in warm colors where it's the highest, actually gets higher away from the fault, which is sort of along the horizon there. And that's that sedimentary basin amplification. And in Santa Rosa, the damage proportionally was worse than it was in San Francisco during this earthquake, largely because Santa Rosa is built on a basin. But these seismic waves travel just a little bit faster than the rupture goes, so they go as fast as an intercontinental missile, faster missile. But the wave speeds are not that, or the speeds of the two processes are not that different. And that leads to Doppler-like effects where you get a concentration of energy in earthquakes in the direction that the rupture is propagating. Okay, so those are the three speeds we have to worry about. The speed of slip, about as fast as a runner, a few meters per second. The speed of the slipping front, perhaps something like 3 kilometers per second. And the speed of seismic waves, depending on the wave, we're talking about 4 to 8 kilometers per second. These are the speeds that are representative of the well-known, what we call regular or fast earthquakes. So these speeds would be considered fast. So in a fast earthquake, the speed of the slipping front, the rupture front, and the speed of the seismic waves is similar. In slow earthquakes, these other speeds, the speed of slip and the speed of the slipping front, are both lower. They're both substantially, perhaps an order of magnitude, lower than in ordinary earthquakes. So that's interesting, and it has consequences for the kind of waves that they generate. So here we're talking about the earthquake from the point of view of an earthquake seismologist who studies the source process. Now we're going to look at how these different speeds translate into a different earthquake signature. So this is sort of our stock and trade. These are seismograms from regular earthquakes. Each one of these horizontal lines, time increases from left to right, and the shaking of the ground is greatly amplified by these instruments and recorded. Here it's recorded on paper, but typically now we record them digitally. And what you will notice is here at 12:50, each one of these represents 10 minutes. So at 12:50 and a few minutes in, there's a very sudden onset to the shaking. So this is the characteristic of an earthquake where the slip happens suddenly and spreads out over the fault quickly. This is a regular fast earthquake. Here's another one that's farther away, and another one as well. These sort of earthquakes are easy to see. They're easy to see on an instrumental record like this. We can pick the times at which they begin quite handily, and we can use that to locate, to detect the earthquake and to locate where it originated from. This is an example of a slow earthquake. So this is a tiny earthquake. It's about magnitude 1, maybe a little bit bigger, but not much bigger. It is recorded on that very sensitive seismic network that I talked about in Japan, where all the stations are buried, all the seismic instruments are buried at least 100 meters deep in the ground. And each one of these are seismograms. Now we're looking at many different recordings at many different instruments. And it didn't translate very well, but the onset is not sudden and abrupt. It sort of emerges from the background noise gradually. So this is the signature of a slow earthquake. It doesn't have a sudden onset. It has a weak and emergent onset. It's actually very difficult to see, and unless you have very sensitive instruments, you probably won't detect these things. These small ones were discovered in Japan after the Kobe earthquake. They were labeled low-frequency earthquakes because they lack the sudden, sharp, high-frequency arrivals that characterize ordinary earthquakes. And the network operators who picked these arrival times were instructed to only save earthquakes for which both P and S waves could be picked. And these did not qualify because they didn't feel confident in picking the arrival time of the P wave, only the later arriving S waves. But fortunately, they saved and archived these events, even though they didn't meet the sort of strict criteria that had been set up for them. So these low-frequency earthquakes were discovered in Japan, and another phenomenon was discovered as well. It's known as was called deep non-volcanic tremor. Deep because it appears to occur at depths of 30 to 45 kilometers or so below the Earth's surface. Non-volcanic because there's a similar sort of phenomena that occurs in volcanoes and is thought to be the signature of moving magnetic fluids in the deep plumbing system of volcanoes. So what's shown here are a bunch of seismograms. So each one of these lines from left to right represents a minute of ground motion. And there's not a lot to look at here, at least at first glance, but if you notice between 30 and 45 minutes during this hour, so there's 60 lines here, this represents an hour, the wiggles, they look chaotic, but they get a little bigger, about twice or maybe 3 times as big. And this was reported by Kazushige Obara, a Japanese seismologist, who was running this sensitive seismic network. He saw these signals and he thought there was something wrong with his instruments. And so he went to troubleshoot the electronics of the instruments because this just looks like noise. This is not something seismologists are comfortable with interpreting. If there's something wrong with the electronics, it can look very much like this. But what he noticed was that this same signal, or a similar signal, occurred at widely spaced seismic stations, and that the signal was delayed in just the right way at one station relative to another to be consistent with a signal coming out of the deep earth rather than something electronic. So he called it deep non-volcanic tremor, and he cataloged where it occurred and where it didn't occur. Its characteristics. He found that it occurred so this is a map of Japan. Each one of these can circles represents a location of a tremor episode, this weak shaking of the ground. He found that it occurred under Shikoku and southern Honshu, but not under northern Japan. This shows that these black lines show when it occurs, and the absence of the black lines shows in calendar time when it doesn't occur. So it's episodic. Sometimes it happens, sometimes it doesn't. But it seems to be very systematic. It happens, what's shown here are the depth contours of the subducting slab, and it seems to happen at about 30 to 40 kilometers depth. Now, I got involved in this sort of work years later. Seismologists sort of grappled with for a long time with how to interpret this signal. What is generating it? Is it the sort of shear slip we have in earthquakes, or is it something else? Is it perhaps something more akin to what happens in volcanoes? And what we were able to show is that this deep non-volcanic tremor is actually a swarm of many tens or hundreds of thousands of these low-frequency earthquakes. So they're actually the same process. It's just when you string together and superpose a bunch of these weak, slow earthquakes, magnitude 1 to 2 earthquakes, you get this sort of continuous rumbling of the ground that's known as seismic tremor. And so how do we establish that correspondence? Well, we use the seismograms. And this is a map. I don't know if you can see it, it's kind of washed out, but this is Shikoku, Japan. Each one of these dots is a place where a low-frequency earthquake is known to occur. There are about 700 of them there. And this set of wiggles at different seismic stations is the unique signature of a low-frequency earthquake at that location. So anytime you get one of those low-frequency, slow earthquakes, little slow earthquakes at that location, you'll get that set of wiggles. So we can sort of sweep through the continuous wiggling in the tremor for this short duration signal. This is just a few, perhaps 10 seconds long, and see where it matches and where it doesn't. So this is, you can think of this as the signature of a slow earthquake in that particular location, just like John Hancock's on the Declaration of Independence. So this is what we do. We have this low frequency earthquake that we know about. We have tremor that we're trying to understand. We, oops, this animation didn't work. Anyway, so basically we slide John Hancock's signature around. If we put it over here, we see it doesn't match that signature, but if we superpose it here, I actually got these signatures from different sources, so the match is not perfect, which is good because it's a sort of a noisy process. But when we can match that signature, then we know John Hancock has signed that document, or the equivalent statement for us, we know that within the tremor there's a low frequency earthquake at that particular location. So here's an example of the equivalent sort of a match. Here we're finding a low frequency earthquake. We're comparing the signatures in red. The tremor signals are shown with the different colors. The colors don't mean anything. They're just meant to distinguish the different traces. And what you can see is that the red pretty well matches all the other signals. So we say that that's a detection. And we could use this to generate a movie or animation of these detections using all these different candidate low frequency or slow earthquake locations. So here is 12 hours, half a day worth of this weak shaking that we call tremor. And the red parts of the seismogram here are places where the tremor and the low frequency earthquakes match. And the dots on the map above show where they match. So we'll just play that. And you can see they tend to cluster in space and time. There's nothing in the detection method that would impose that. That's something that is required by the data. It's about to get much more active in this section here. So, and this one gets very active right at the end. Okay, so this is the evidence that tremor and low frequency earthquakes are the same thing. And we can, so now we have a sort of Rosetta Stone for tremor. We can pick it apart and say all sorts of things about it. There was very quickly, at about the same time really, there were other discoveries that were made. VLF, that stands for very low frequency. So these are earthquakes that are slower still. These low frequency earthquakes, they take about a second to occur, even though they're magnitude 1. A typical magnitude 1 earthquake might take a few hundredths of a second, but a slow magnitude 1 earthquake takes maybe a second. These very low frequency earthquakes are slower. They take something like 10 to 100 seconds to occur, but they're bigger. They're magnitude 3 to 4, so they involve a larger fault, and this is the signature of a very low frequency earthquake at a set of sensitive seismic instruments, also in Japan. We discovered an even slower set of earthquakes. We should have called these ultra low frequency earthquakes, but we called them very, very low frequency earthquakes, what we were thinking. But these are even slower, so they're over 100 seconds period. It turns out the Earth is noisy, gets increasingly noisy at longer periods. And so it gets harder and harder to see things of an equivalent size. So we were only able to see these because we had a very sensitive, well-behaved seismic instrument, basically right on top of where these things were occurring. These are slower, 100 to perhaps 200 seconds in duration, but they're larger. They're magnitude 4 to perhaps 4.5. Now, any larger than that, and the seismic waves sort of disappear into the background seismic noise. So we have to turn to geodesy, that is the study of the change of shape of the Earth's surface. And geodesy measures how the Earth deforms over very long time scales, so from tens of, well, you can do it at 1 second period, but typically it's done over periods of weeks to months to years. And this is an example, so GPS is sort of the way that most geodesy is done these days. This is, again, a figure of Japan, and it's covered with red arrows. Those red arrows are showing how the islands of Japan are deforming, the velocity at which different points on the Earth's crust are moving in between earthquakes. So what's happening in Japan is the Philippine Sea Plate is crashing into southwest Japan at a rate of about 4.5 centimeters per year. And as it does so, there's a strain or a change in these velocity vectors from being very large on Shikoku to being very small on Honshu. So Japan is changing its shape. It's storing energy, and that change in shape in the form of potential strain energy that will eventually provide fuel for earthquakes. Here in northeastern Japan, it's the Pacific Plate that's crashing into the Japanese archipelago, and it's going about twice as fast, or something like 8.3 centimeters per year. And you can see a similar pattern. You can see the arrows are longest, velocities are highest here near the coast. They get shorter to near zero, near the Japan Sea. This is, again, the signature of strain accumulation on a locked plate boundary. Now, what I'm going to show you here are GPS measurements that were taken during the March 2011 earthquakes. And what will be shown on the left, so these are sampled every second. What will be shown on the left is the horizontal motion. And this is an arrow of this length is 1 meter, so over 3 feet of motion horizontally. What's shown on the right here is the vertical motion. There's more uncertainty in the vertical than in GPS, but you'll be able to see separately the horizontal and the vertical motion. The earthquake, when it occurs, is going to be shown with a red star offshore on both sides. It will take some time for the seismic waves and the deformation to propagate onshore. You'll be able to see the change in the rebound and the motion in the opposite direction to what we saw before. And, well, just let you see it. Okay, so the earthquake happens, the waves are propagating towards shore. Japan starts deforming. You can see waves propagating through this field, in the horizontal and in the vertical. And notice that the arrows don't go back. So Japan changed its shape massively in response to this earthquake. The longest vector here is something like 5 meters long. There's a magnitude 7.9 earthquake that occurred a half hour afterwards. Really very much smaller than the magnitude 9 earthquake, although a big earthquake in its own right. So the shape of Japan was different because of this earthquake. The entire coast dropped by up to 1.5 meters. So the tsunami came in on top of that, the lowered coastline. The deformation offshore, those vectors, instead of being something like 5 meters, or there's a few places where they were able to measure them using seafloor based geodesy, and they're as large as 23 meters. So it's that change in shape that led to the deformation of the seafloor and the excitation of the devastating tsunami. But for the purposes of this talk, I'm just using that to illustrate the difference between strain accumulation between earthquakes and strain release during earthquakes. So this is a zoom in on the northern part of the Honshu coast before the earthquake. This was its deformation. This is the deformation during the earthquake, or as a result of the earthquake. You can see here the arrows point to the west-northwest. Here they point just about the opposite direction. If we make one transparent, we can see that they're in opposing directions. So strain accumulation points one way, strain release, or the occurrence of an earthquake, points the other. So now we switch to what you and I call the Pacific Northwest. I gave this talk in Canada, and the people who did this study are Canadians, and they insisted this is actually the Pacific Southwest. But what they were able to show, using the same sort of GPS-based geodesy, although notice how the distance between instruments and vectors is much, much larger, they were able to show that during earthquakes, as well, or between earthquakes, the arrows point in the direction of plate convergence, that's strain accumulation. But during brief episodes that lasted perhaps a couple of weeks, those arrows reverse, that deformation reversed in direction, consistent with the occurrence of an earthquake. However, there weren't any seismic waves radiated because these earthquakes occurred so slowly that they didn't generate seismic waves. But they're big, they're extensive. The equivalent magnitude for earthquakes in Cascadia, like this, these slow earthquakes, we call them slow slip events, they're up to about magnitude 7. The largest known one occurred in Mexico, and it's about magnitude 7.5. So these are big events, or they, in the traditional sense, but they occur so slowly that we didn't even know they were occurring 15 years ago. So we now have this sort of menagerie of these slow slip processes. We have the low frequency earthquakes and the tremor, which we've said are the same thing. We have the very low frequency earthquakes, the very, very low frequency earthquakes, the slow slip events. Once they were discovered in, I'll just say it, the Pacific Northwest. Once they were discovered here, the Japanese looked more closely at their geodetic data, and they were able to see them there as well. They're smaller there, so they're harder to see. But these various kinds of slow earthquakes, they're all occurring on the deep extension of the subduction zone. They occur at the same time in the same place by the same mechanism, and so it's natural to say that they're the same thing. They're all slow earthquakes. And they were all of these were discovered in the last decade plus, so since the year 2000. And if we plot the seismological measure of earthquake size, seismic moment, we could use magnitude as well, versus earthquake duration, ordinary earthquakes follow, and this is a log-log scale, ordinary earthquakes follow what we call a particular scaling. So they have a power law scaling, which means that we can fit them with a straight line of log-log space. The slope of this line is 3, and that means that as an earthquake, a regular earthquake increases in duration. The longer it ruptures, the bigger it gets, and it gets bigger really, really quickly. So it grows with the cube of the duration. So an earthquake that takes twice as long is 8 times as big as the earthquake is being compared to. Slow earthquakes are different. So these are the various slow earthquakes we talked about. The slope of that line is 1. meaning they grow linearly or proportionally to their duration. They don't have this sort of explosive growth. Now, I like to compare this to astronomy. This is a scaling diagram for stars. It was presented in London in 1912. It shows luminosity on the vertical axis versus color on the horizontal. And what astronomers noted was that there were certain areas that were densely populated with stars, and other areas that were completely devoid of them. And they didn't know why stars behave this way. It was not yet, fusion had not been discovered. It wasn't known that stars were mostly hydrogen. I'd argue that we're sort of where astronomers were back then. We have this very interesting behavior that we see in earthquakes, a scaling diagram. We don't yet know what it means. So how can we figure out what's behind slow earthquake behavior? Well, one important way to do that is to look at the systematics of that behavior. So how it varies with, say, subduction zone, convergence rate, temperature, composition, all sorts of things like that. So we look at the geography of slow earthquakes. And we're in the early stages of doing that. In Japan, so what's shown in green are the geodetically observed slow slip events. In red is the tremor, or the short, the low frequency earthquake swarms. They're occurring in roughly the same place. What's shown in pink are the rupture zones of the last two magnitude 8 earthquakes on that part of the subduction zone. And what you notice is that these two fields roughly abut one another. So the slow earthquakes occur immediately adjacent to the fast earthquakes, just a little bit deeper. In Cascadia, we don't really know how deep the rupture zone is going to be in large earthquakes. As you know, the last big earthquake here was in 1700. But there are a lot of slow earthquakes happening here. What's shown in green are the documented slow slip events. In red, the tremor. It's reasonable to expect that the rupture zone in future earthquakes might approximately correspond to the up-dip limit, or the shallow limit, of these slow slip events. In Mexico, we have both, but the behavior is neither here nor there. It's a little more complicated. Guerrero is where the very biggest slow slip events ever observed are, magnitude 7.5. The tremor, these locations are much more uncertain, but the tremor so far seems to be deeper, and the slow slip events shallower and disjunct, and then the ordinary earthquakes, the fast earthquakes shown in pink, closer to the trench, are shallower still. Costa Rica, there were just a couple of big earthquakes there, so this story is probably going to evolve, but they seem to be all sort of tangled up and intermingled there. So the story's not simple, and there's more to be done. So you're too polite, probably, to ask this question, so I'll ask it, and that is, why should we care about slow earthquakes? Well, I think they're cool. So I mean, it's just like astronomers discovering neutron stars and pulsars and quasars and things like that. This is a different kind of phenomenon. It's happening under our feet. It happens right under us here. And 15 years ago, we didn't know it was happening. So it's just intrinsically interesting for that reason. And take a look at this. So what's shown on the left, this is from Mike Brzezinski. This is an animation of the ordinary earthquake activity. This is the slow earthquake activity. And it does really interesting things. It turns out that slow earthquakes in the Puget Sound region happen almost like clockwork. They happen every 14 months, plus or minus 1 month. And they're so regular that seismologists plan to go out in the field to record the earthquakes before the earthquakes happen. So they happen on a schedule. And if only ordinary earthquakes were so regular, our jobs would be a lot easier. We wouldn't be thrown in jail. We're getting things wrong. So another reason to study slow earthquakes is that they occur on the same faults by the same shear slip mechanism that regular earthquakes do. They occur in this transitional region, so they have potential to tell us a lot about the hazards that are posed by ordinary earthquakes. So this is a cross-section of Cascadia, showing the lock zone along the coast and offshore, showing the slow slip region immediately down dip from that. When these slow slip events occur, it's inevitable that they will increase the stress at a higher rate on the locked part of the fault that all of us worry about. So it's natural to expect that these two phenomena ought to be spatially and temporally correlated. That correlation has not yet been established, but it's something that we're really interested in exploring. If this correspondence between the slow slip zone and the regular earthquake zone that's seen in Japan can be exported to other parts of the world, it gives us a really valuable bit of information. It tells us how far down dip or how far inland these large subduction zone earthquakes will rupture. The farther inland it ruptures, the stronger the shaking, the closer the shaking will be to cities, and hence the stronger shaking to be expected from future large earthquakes. And here in Cascadia, if you assume that that correspondence applies, then the region of high slip in future megathrust earthquakes on the subduction zone will be something like 75 kilometers farther inland than is currently assumed in the National Seismic Hazard Map, which is shown here. So those areas of red, the very highest seismic hazard, will move something like 75 kilometers inland and much closer to Portland and Seattle. So even if it doesn't tell us anything about forecasting earthquakes, it tells us about forecasting earthquake shaking. Because these occur by the same mechanism as earthquakes, only slower, they still generate seismic waves, and we can use those seismic waves. This is work that my only postdoc is doing, using recordings of the tremor in Cascadia to predict how this is a log of seismic intensity versus distance, this population of points, which is shown in the color scale, shows how the amplitude of seismic waves decay with distance. And that's really important information for constructing these kinds of maps. And we're starting to be able to use tremor for that purpose, these slow earthquakes for that purpose. It's telling us new things about other faults, these slow earthquakes. It suggests that we get shear failure, that is slip-on faults down to 25 kilometers depth, much deeper than had been previously assumed for the San Andreas Fault, and that's important for assessing the hazard and the shaking from future earthquakes on that fault. And in places like Alaska, where we have relatively little information on earthquakes, the tremor is actually helping in this. So this is I don't know what part. This is southern Alaska, right? I don't know my Alaska geography well. I think this is the Cook Inlet, but there's a part of the plate boundary that's not well understood. There are no earthquakes occurring on it right now, but there are these small, slow earthquakes. So it's possible that these slow earthquakes can help us to delineate plate boundaries where that information is uncertain, but of course important. And it's also worth mentioning that I focused my talk on areas that, like Japan and Cascadia, where there's good earthquake monitoring, but for much of the world, it's effectively unmonitored. That is, there are all kinds of earthquakes occurring in places like Sumatra, Tonga, you name it, where we just don't have data in close to tell whether these slow earthquakes are occurring and what their relationship might be to the ordinary earthquakes that are occurring in those places. So I'd like to wrap up by saying, returning to the Kobe earthquake, and saying that these discoveries were enabled by a a commitment to improved earthquake monitoring, and this led directly to the discovery of slow earthquakes. I can illustrate this. This is in the 2 years before the Kobe earthquake. This is the Japanese earthquake catalog. This is in a 2-year period well after the earthquake. There are many more earthquakes shown here versus here. It's not because more earthquakes are occurring, it's because they have a better monitoring system. And the red in this plot are these slow earthquakes that were previously not even known. So IRIS, one of the sponsoring organizations for this talk, is currently running a part of the EarthScope program where they're doing earthquake monitoring across the continental US. There's a proposal planning to take those, most, not all of those stations, to Alaska to monitor earthquakes up there over a 5-year period. And there are longer-term ideas for improved monitoring in Alaska, Cascadia, other part, Middle America Trench, and South America, basically the whole eastern Pacific Rim, in order to look at the systematics of earthquakes, slow earthquakes, and associated phenomena. So I'd like to conclude by saying there's this family of slow earthquakes that we didn't know about 15 years ago. They present all sorts of new research opportunities that people like me are just beginning to exploit. New monitoring leads to discoveries, and that's a consequence of the fact that earthquake science is still a very young field. So we're still making fundamental discoveries, and it's despite what happened in Italy recently, it's a good time to be a seismologist. So I'll stop there and take your questions.